Good morning, everyone, and welcome to the Matrix AI Spring Seminar Series. Today, we're pleased to host Dr. Amey Kulkarni. Dr. Kulkarni is currently working as a deep learning engineer at NVIDIA. He's focused on neural network optimization schemes for improving hardware efficiency. Before Dr. Kulkarni started at NVIDIA, he was working as an FPGA engineer with a DSP and computer vision focus at the Research and Development Labs of Velodyne LiDAR in San Jose. At Velodyne, he developed generalized neural network architectures to improve accuracy of current and future LiDAR products and build image processing-based hardware and software for Velodyne's automated alignment systems. He received his PhD in computer engineering at the University of Maryland, Baltimore County. His main research focus is on designing real-time and low-power hardware architectures that are resource-efficient, cognitive, and trustworthy. He's actively researching strategies to efficiently perform computer vision and signal processing algorithms acceleration using hardware platforms, particularly FPGAs and multiprocessor systems on chips. During his academic career, Dr. Kulkarni has published over 18 papers in peer-reviewed conferences and journals and has over 450 citations. Thank you, Dr. Kulkarni, for presenting today, and we look forward to your presentation.
Yes. Let me share my screen and let's get started. So I think all good. So yeah, thank you, Henry, for kind introduction, and I think thank you to UTSA and Professor Kuditipudi for giving me this opportunity to share some of my experiences on deep learning inference optimizations for embedded platform. These experiences are mostly gained from my PhD. I did a PhD in computer engineering and my past employments. And I must say, NVIDIA played a huge role in honing and improving my skills on this topic. So before we dive into presentation, I just wanted to read this disclaimer that views, thoughts, and opinions expressed while presentation and QA belong solely to myself and not necessarily to my employer NVIDIA. So today, as the topic says, I would like to speak on deep learning inference optimizations. And I hope that students have some background on deep learning. And for students who are new to deep learning, we'll have a quick glance at deep learning before diving into the optimization technique. So then I will discuss about importance of DL optimizations, why we need to do like DL optimizations for embedded system, and eventually I'll go over some of the NVIDIA toolkits to efficiently deploy deep learning models on NVIDIA embedded platform, also called as NVIDIA Jetson. So yeah, so here's the quick clue. So picture actually shows the diagrammatic picture of computational neural network, or rather deep learning with the convolution neural network. So here the basic idea is that the neurons in the input layer receive some values and propagate them to the neurons in the middle layer of the network, which is also frequently called as a hidden layer. And the weighted sums from one or more hidden layers are ultimately propagated to the output, which presents the final output, or you can say the results, predicted classes to the user, basically. So basically, overarching goal for training the deep learning model is to determine the weights that maximize the score of correct class and minimize the score of the incorrect class, right? So today, so every neural network has a multiple convolutions and fully connected layers. And as you can know, like you might know, the more than 90% operations are multiplications. And that's where GPU can come in handy because GPU is known for doing matrix multiplication efficiently. So just to give you an idea, today the typical number of layers in a deep learning model can range from 5 to the more than 1,000 layers, right? So that's a quick understanding of what deep learning or what is the complexity of deep learning. So let's first understand what is the difference between the cloud and the edge. So edge is also called as embedded platform, right? So cloud is the platform where users can have like access to abundance of computational resources and data storage. And thus there is no direct limitation on power consumption or even number of resources being used. Whereas embedded system is also called as edge platform, has lower computational resources and limited memory storage in processor hierarchy and external memory. And so now by this definition of cloud and edge itself, it's much clearer to understand where we can train the deep learning model versus where we can do the inference on deep learning model, right? So why really, right? So in training, training a DL model requires high compute resources, right? As it needs to compute the partial derivatives, right, of gradient based on a chain rule, also called as backpropagation, right? So this comes with the multiple weight updates and thus require multiple storage copies of model weights, basically. So furthermore, DL model training requires large data sets, and thus cloud platform is an ideal fit for deep learning training. Whereas for inference, it needs comparatively low resources as it performs forward propagation only, right? We don't need to do any back propagation now. So however, if the cloud has already computational and storage resources, then why we should switch to the edge platform, right? That can be a question. So in most application, it is actually desirable to have a near sensor processing. So let's take an example of traffic monitoring system, right? Such as anomaly detection, where you try to understand if a vehicle is taking a U-turn where it's not necessary, or a vehicle is actually going into the wrong direction or getting into the wrong way, right? Then there is a vehicle re-identification. You have a multiple cameras at the traffic, and you're trying to basically identify the same vehicle for speeding or any other thing, right? So these kind of application, you need right at the image sensor, because the latency requirements are stringent, and also the security risk of relying on the cloud is too high. Like also, like let's say another example of basically security cameras. I mean, this is pretty. Most of us have security camera at home, and most of the security cameras are still using cloud for performing like person detection or motion detection, and therefore you will see always a significant delay between a person passing by the camera versus actually getting the notification on your cell phone. So these are like some of the like advantage of being on edge and versus being on cloud, right? So I think so I just wanted to go over first like what are the challenges, and that we'll cover in this particular section. So as we discussed in the previous slide, it is highly desirable to have like application running at edge. However, most of the video processing application involves a huge pipeline, such as there is a sensor interface, there's a pre-processing of the image or data you receive from the sensor, and then there is a, let's say, DL model or a high complexity computer vision algorithm, and then followed by the post-processing that can be clustering, or that can be understanding more correct classes, let's say. So thus it involves large amount of memory transfers and computationally complex process, which enables the so thus enabling the embedded system with a strict requirement is basically challenging, but yet critical to the enabling these applications locally. So embedded platforms typically have low computational resources and low memory in processor hierarchy. And in most of the times, it requires to be operated on the battery. So in most cases, in some application, form factor is also important, such as like if you consider fitness tracking devices like watch or your cell phone or security cameras. So let's focus on like robotics or self-driving car application, because that's more apt for embedded applications. So most of you might know like SLAM, or simultaneous localization and mapping, which basically constructs and updates the map of unknown environment while keeping the track of its location in it, basically. So SLAM required to be accurate up to 2 centimeters. And another application like this, which has stringent requirements, is like dynamic obstacle avoidance, right? That requires up to plus or minus 1 centimeter accuracy. So these applications need to be performed at edge, right? That is, robotics needs robotics needs like a highly complex, and as you can see, like a multiple deep learning model deployment while being real time, that is maintaining at least 30 frames per second or higher, right? So these detections can be performing on different sensors. So as you might know, like most of the robotic platform has a multiple sensors. They have LiDAR, they have radar, they have a IMU, they have camera. So these detections can be performing on different sensors that it needs a graph allocation and demand for multiple memory inputs, basically. So one of the most attractive tasks in in basically robotics, I'm giving here example that is called as instance semantic segmentation, in which each image is, or each image pixel is assigned to a class as shown in the image, right? So here you can see there's a each image is being assigned to car, like in a blue color. There is a road sign in the yellow. There's a free space, which is magenta, I guess, and then there is a pink, which is non-drivable area, or it's not a free space. So there are multiple classes here, and in most cases, input images are maintained at a high resolution for meeting the accuracy standards, right? And instant segmentation. So basically, this particular models are being used in free space identification, dynamic obstacle avoidance, road sign understanding, and also lane keep assistance. So there are multiple applications for this. But this application has this particular model has a higher computational need and also depend on higher input image size. So this model needs also the image segmentation needs receptive field dilation for improving accuracy, which needs higher memory. So all in all, you can see like for the robotics platform itself, you have a lot of stringent requirements on it, and with the highly complex tasks, right? So you need to optimize these tasks, right? All right. So I think so. In this, to optimize the whole task, it needs to be a cross-team effort, right? So it's not only done during the inference, but in some cases also during the training time, right? So it has to be basically sensor interface has to be right, accelerator architecture has to be right. You need to perform algorithm modifications. You have to have a software which is targeted towards your hardware or hardware specific software, and then definitely it sometimes can go into the circuits as well, right? So to optimize this effectively, you need an end-to-end workflow, and like basically the support is needed for it. So let's basically say for sensor interface, for example, there is a CSI NIP interface for camera input, and with the pre-processing of GStreamer software stack, or in case of LiDAR, you need to have accelerated point cloud library to basically have gather this data and process it efficiently, right? For accelerator side, this is the NVIDIA, one of the GPU architecture I'm showing here. So for architecture, you need to have like a pre-processing and post-processing, and the GPU with a DLA or deep learning accelerator for deep learning workloads. Then there is a vision processor interface, which is called as VPI, or NVJPEG, or image pre-processing hardware specific kernels, right? And then you do algorithm optimization such as pruning or quantization, which we'll discuss in this talk. And then there are hardware specific software modeling. So this particular picture, software picture, it shows like a workflow for NVIDIA TensorRT. And that is being used for optimizing the kernels post-training. So in today's talk, I'll be focusing on some of the algorithm techniques to improve the DL performance, including quantization and pruning. I'll go over it briefly. All right. So first is quantization. So quantization is considered as one of the major approximation theme in model optimization, and thereby increasing the throughput and by reducing the reliance on slow off-chip memory. So floating point quantized deep learning model typically allows for an arbitrary binary point, as you know, that is exponent value and each individual parameter. However, this flexibility in data representation comes with the expense of high resource use and power consumption and arithmetic operation latency, right? Whereas fixed point quantized deep learning model generally uses consistent and predetermined precisions and binary point locations, and that is equal maximum and minimum representable magnitudes for entire network. So this allows for fast, cheap, and power efficient arithmetic operation in hardware, but enforces the use of constant data representation, right? So therefore, there is a accuracy versus latency trade-off, right? So it's becoming so in today's recent research, it's becoming commonplace to basically train a neural network on 16-bit floating point format, and either in FP16 or let's say pfloat16. And those are supported by most of the DL accelerator, and then basically do the quantization later. And there are two different techniques to basically perform deep learning model. First is basically called as post-training quantization, right? So it's called as, I'll just separate it as PTQ. That is once deep learning model is trained, neural networks can be basically deployed for inference using even lower precision formats, including floating point, fixed point, or integer formats, right? And then there is a second one, which is called as quantization aware training. So this describes the technique of inserting quantization operation into the neural network before training or fine tuning to allow the network to adapt for quantization weights or activation. And so both of these techniques offer several performance benefits. So first is most of the processors provide high throughput math pipeline. The math pipelines, the low bit format, right? So which can speed up the math intensive operation such that convolutions and matrix multiplications, right? So second one is smaller word sizes reduces the memory bandwidth pressure, improving the performance for bandwidth limited computations, right? The third one is basically smaller word sizes lead to the lower memory size requirement, which can improve the cache utilization as well as other aspects of memory system operation, right? All right, so to quantize a value, it comes to this particular equation, which is called as R equal to S into Q minus C, where R is basically the real number and Q is the quantized value, and S is the scale and Z is the 0 point. So where S and Z, we call it as a quantization parameter. And these quantization parameters are basically essential for minimizing the information loss when converting from higher precision to the lower precision, right? So Q parameters needs to be learned by your quantization method. It can be either PTQ or it can be quantization aware training quad, right? So let's go over like quickly what is the workflow for doing PTQ or QAT. So in post-training quantization, as shown in the first, like the upper image, it starts with a pre-trained model and evaluate it on the calibration data set. So you have a part of the training data set, which is called as a calibration data set. This calibration data set can be a subset of training data, which is used to calibrate the model, right? During the evaluation, we could gather layer-wise statistics and calculate like a dynamic ranges of weights and activation in the network. And these dynamic ranges are then used to compute your quantization parameters like S and C. And finally, we use these quantization parameters to quantize the network to perform the inference, right? So you are learning through the iterative process, basically. You basically try to understand what is your dynamic range, and that's how you go about it, right? So, and then there's a QAT, which was actually introduced in TensorFlow, in which Q parameters are learned during the training. So the workflow is we would start with like a pretend model and introduce quantization ops at the various layer. You can also, they also say it as a fake quantization. We fine tune the model for a small number of epochs. And then dynamic ranges of weights and activations are learned during this training phase process and used for quantization ops, right? This simulates the quantization process that occur during the inference. So basically, you're trying to emulate the quantization process. And eventually, the goal is to learn the Q parameters, which can help to reduce the accuracy drop between the quantized model and the pretend model, right? So let's go like quickly on what are the like significant differences between the PTQ and QAT. So post-training quantization is usually fast. It depends on number of calibration data samples being evaluated, whereas QAT is really relatively slow, as we need to fine-tune the model. So it's an iterative process. So therefore, there is an investment in training time, basically, right? PTQ does not need any retraining or fine-tuning of the model. We can plug in different quantization scheme and compute Q parameters in PTQ technique. However, for a different quantization technique in QAT, it needs a retraining of the model. So each model needs to be retrained too. So it's not plug and play, basically. With post-training quantization, we have less control over final accuracy of the model, whereas in QAT, we have more control over the minimizing the accuracy difference. So, okay, so let's say I completed the PTQ. So how can we improve the accuracy more, right? So when post-training quantization does not meet accuracy requirement, we can do actually two things. So one is to trade off the performance for accuracy by doing the partial quantization, that is leaving some of the layers in the in FP32 or FP16 precision. So in my experience, most of the networks have few layers that are more sensitive to the quantization. In this, we can quantize each layer individually and run inference to determine which layer contributes most to the accuracy loss, right? And then we can iteratively leave sensitive layers in the floating point to increase the accuracy until the target accuracy is reached. So this is called as like a mixed precision. So you're basically using some of the layers in FP32, FP16, and some in date maybe, right? The second one is actually, or more sophisticated, is basically quantization aware training, as we were discussing. So in this, the neural network training typically uses, so basically why we need to do QAT, right? So in neural network training, typically uses like a stochastic gradient descent, which attempts to minimize a given loss function, right? So problem with the post-training quantization occur when this converges to a narrow minimum, meaning that slight chance in weight or activation value due to quantization will lead to the big increase in the loss, right? So I think in this figure, so consider the one-dimensional loss function shown in this upper left figure, where orange point is original, whereas blue circle is quantized point. This we can see that the loss increased by 0.5, which significantly affect the accuracy, right? So where quantization like QAT helps. So quantization technique avoids this by computing the gradients at quantization point, meaning narrow minima will produce a strong gradient, which can push a model out of narrow minima. Thus, quantization point will have a lower loss, and thus this should give us like a higher accuracy, basically. So that's where QAT will help. And now here's like some comparison between the PTQ versus QAT. This I'm actually getting from one of the research paper from NVIDIA, and also this is presented in one of the GTC talk. So basically, you can see here, QAT is almost performing better on all the major state-of-the-art networks. And even if the loss, like if there is decrease in accuracy, it's within certain threshold, basically. Whereas PTQ can see significant accuracy loss, such as in mobile net or efficient net, or rather in transport or transformer, basically. All right, so I think let's go over like the second technique, which I was mentioning, that is called as pruning. This will be a very brief introduction to the pruning, and that's where we will go into the more practical implementation later. So why we can do actually pruning of deep learning models, right? So here basically parameters which are deemed unimportant are ultimately eliminated entirely, right? So weight reduction improves the performance of inference by reducing both workload and off-chip memory transfer. So this has definitely a huge advantage when it comes to memory storage capability, right? So why we can prune model? So state-of-the-art models are over-parameterized, such as let's say VGG16 has 138 million parameters. AlexNet had, I think, 61 parameters. These can lead to optimization failure, such as some of the neurons are dead, that is, it's having a little activations, and some of the neurons can produce uncorrelated output, right? So therefore, removing redundant connections can actually improve the accuracy. So pruning basically removes the unnecessary connection, thereby reducing the memory resources or transfers, reducing DRAM access, and that helps tremendously in reducing energy consumption. So this is just to give you an illustration of scale. This picture I actually saw in one of the TinyML talk, and which is pretty exciting. Let's say you have basically a word in SRAM cell in Iris neural network chip, which is actually MIT chip if I'm not wrong, that needs to travel about 4 mm across the chip. Let's compare that with the car traveling analogy. And your car is like 5 meters, so therefore so to pull same amount of effort, a car needs to travel, let's say from your university till Austin, or approximately that distance, right? So now pruning will actually will reduce some like this distance, and therefore your basically transfer time will actually be reduced a lot. All right, so transfer learning basically supports state-of-the-art accuracy, right? So however, inference is expensive due to the time, power, memory, and demanded by the heavy weight architecture of fine-tuned network, right? So for small data sets, let's say example of Microsoft cats and dogs, that's what I'm showing the image. If trained on 4-layer neural network, can result in lower accuracy. So you have a small network, you have a lower accuracy now, but the model size is pretty good. So you're maybe happy with the embedded inference, right? So in most cases, to learn the objective from small data set, model needs to be fine-tuned, right? Or transfer learning is required, basically. However, fine-tuning on the large pre-trained network will result in better accuracy. However, inference using large model will not be efficient on embedded platform. That's the second scenario here, right? Your accuracy will be good, but the model size can be bad, and therefore inference on embedded might be tricky, right? So now with the goal of speeding up inference, what we do is we perform the pruning after fine-tuning process. So basically you have a large network, you perform a fine-tuning, therefore your accuracy will be pretty good. And then you remove the dead neurons by pruning. And now you have basically good accuracy and a good model size, right? So that's the brief idea of pruning. So let's go about like a typical workflow of pruning a deep learning model. So pruning is an iterative process in which the goal is to attain the state-of-the-art accuracy while reducing the number of parameters or connection, thus enabling faster inference on the embedded systems. So a typical workflow would be as shown. Like so, first fine-tune for a small data set and estimate importance of neurons and feature maps. Then rank the units according to importance, that is based on accuracy impact. Based on accuracy, remove the least important units, and then fine-tune the network for, let's say, k iterations, right? Check the accuracy of the network. If it is comparable to the state-of-the-art network, test the performance on embedded systems. If one of these criteria does not meet, then go back to again start and do the fine-tune again. So basically, this is the iterative process, right? So you try to look for a satisfactory accuracy. If this is good accuracy, you actually go, you get the pruned model. If not, you go back to the first, start fine-tuning. So this is kind of a iterative process. So I think, so what to expect after pruning? So pruning is an iterative process in which the goal is to attain the state-of-the-art accuracy while reducing the number of parameters or connections, thus enabling the faster inference. That's the gist of it, right? So immediately after the pruning, we can evaluate the smaller model again on my validation data set. Several cases basically can occur, right? So the first is the metric barely changes. So this is what most of the time I observe in basically. So despite removing many neurons, the model performs equally well, right? The metrics improve basically. So in this case, basically it's relatively rare, but pruning is another regularizer which may help combat the overfitting or basically improving the model ability to generalize. And then the third is basically it deteriorates, right? So you might see a dramatic loss of accuracy. And this may happen if we accidentally remove some of the useful neurons, right? But however, if I keep training my model, I can see that the model quickly recovers in large majority cases, performing as good as like original model, right? So that's about pruning. Basically, I'm just giving a brief idea of what pruning is. So I think let's go to the practical guide to basically doing this DL optimizations. So in this, I'll go over some of the NVIDIA specific tools to optimize DL models in which models in much easier way, basically. So first I'll go through the like TensorRT, which is NVIDIA's DL framework or deep learning framework to perform the different post-training optimizations. And then I'll go through the end-to-end DL optimizations for using the NVIDIA transfer learning toolkit. So from the software side, NVIDIA gives you like a full complete end-to-end optimization. So the typical workflow for training and inference could be first you gather data set which is less noisy and higher background variance, right? Then perform the image decoding and pre-processing, basically, or traditionally this is basically performed on CPU using basically libraries as NumPy or scikit-learn or Pillow. However, in case of large data set, this can actually result in CPU bottlenecks and therefore reducing the training speed, even though basically you have a good or ideal GPU, right? So what you do in this case is basically you can use NVIDIA data augmentation library that is called as DALI, and it has a much simpler integration to widely used frameworks such as basically PyTorch or TensorFlow. The next phase is to perform training DL model. As we were discussing, right? So quantization aware technique. NVIDIA has a library called AMP that is called basically automatic mixed precision library, and that basically that is also integrated with TensorFlow or PyTorch, or actually more networks, more frameworks. And then eventually for inference optimization, you will go through, you can use TensorRT, which I'll focus in upcoming slides actually. So let's dive into like a little bit into TensorRT basically. So NVIDIA TensorRT is a programmable inference accelerator. So the workflow is as shown in like the figure above, right? So basically, if you have a trained model using TensorFlow, Cafe, PyTorch, it will use the different optimization technique to get a optimized engine file for embedded platform, and it basically allows you for layer fusing, where it can perform vertical or horizontal layer fusion, thus reducing the number of connections and hence memory transactions. Then you can do kernel auto-tuning, and is performed using understanding the best performance of the target GPU. This can be gathered using input data size, path size, and memory, that is parameter size, etc. Right. So tuning is performed based on the underlying hardware, so it is hardware specific. And then you have a precision calibration. So as we discussed previously in post-training quantization, with the calibration, so calibration can be performed using TensorRT in this. And finally, it reduces the latency by allocating basically dynamic tensor memory, right? So let's take a case study. So basically, this is an example of GooglyNet. This was actually presented in one of the GTC talk last year from the Jetson group, I guess. So in this, so first it performs vertical fusion. So basically, you can see here some of these layers are basically fused vertically, which can increase the throughput significantly. Another feature is basically horizontal fusion. So fusions basically. So adjacent layers which share the same structure can get merged into one kernel, and then split them at the output. So this will reduce the kernel launches to the model. Right? So other modification include like post-training quantization. So TensorRT allows FP16 and int8 model optimization based on the underlying GPU. So this is basically the visual profile of using the PyTorch, basically. So of GooglyNet model deployment. So both visualization and statistics are available with the NVIDIA Visual Profiler. So basically, you can see kernel execution timeline on the left. As you can see, the GPU utilization is relatively low, given all the white spaces where kernel on GPU are not being executed, right? So these are the white spaces you can see. So figure on the right shows types of kernel execution statistics. So maximum number of invocation is about 57, showing that the potentially less fusion occurring in the model, and similar methods are called over and over, right? So and then you have this TensorRT visual profile, and now we can see GPU is being highly utilized. So you can see the compute row here on the left, in the left figure, and it's almost, there is no downtime for the GPU. And in the right side, you can also see the kernel invocations are lower, so maximum being 11, right, and average is being 2.7. This indicates that the overhead from the kernel launching is much smaller. So that's where you actually improve the performance using TensorRT on the embedded platform. So I have been seeing embedded platform from NVIDIA Jetson. So let me go over quickly for like the Jetson family overview. So there is a Jetson Nano. This was the smallest in terms of form factor before arrival of Jetson Xavier. And now Jetson Nano and NX both share same form factor as 45 mm by 70 mm, right? So Xavier and Jetson Nano is available right now for 4 GB, I think it's 99, and then for Nano 2 GB, it's much lower price. So Xavier NX provides like 21 tops with the intake at 15 watts and 14 tops at about 10 watt power consumption. So the application that require highest level of compute platform, we have a Jetson Xavier, which provides like a 32 tops at intake at about 10 to 30 watts. So this is just a quick family overview. You can find out more on NVIDIA Jetson website. But now that we understand the TensorRT and now we know what are the Jetson platforms, we can compare the performance statistics. So it shows that for most of the kernel, TensorRT improves the FPS by about 1.5 to 2 times on Jetson Xavier due to higher computational resources and memory size. We can go for a higher batch size, that is basically increasing the parallelism, and thus basically improvement is much higher in case of 2 to 10 times, right? So you can see like TensorRT is actually giving you a much higher advantage. All right, so remember, eventually we want the model to be accurate, lightweight, and should perform the real time, right? So, however, like challenges for most developers or coders is it needs a learning or expertise in one or more deep learning frameworks or CV or computer vision or ML libraries like OpenCV, sklearn, etc. And there is no straightforward API to basically optimize the model for inference using training frameworks. At the same time, one needs to collect large amount of data for a better accuracy. So all in all, let's say, so whatever we discussed till now, let's say if I give you one tool to do all of that and with a one-line interface. So there is no code approach, basically. And that is called as basically NVIDIA's transfer learning toolkit, and that is basically TLT abbreviated as. So we went over like lots of concept, and I can understand that this can be overwhelming to understand and deploy on embedded platform. So if we have an API to perform all the techniques using one-liners, so basically to use TLT, you do not necessarily have to know all the concepts in depth, such as transfer learning, pruning, quantization, and so on. And these simple toolkits abstract away complexity, allowing you to focus on your application, basically. So here is the example. We built basically a face mask detection using the transfer learning toolkit and deployed it on Jetson embedded platform. This was for basically security cameras where you want to see if a person entering your facility is wearing a face mask or not. So we follow basically the above workflow, and I'll discuss in next slide. And then here are some of the GitHub links and more discussions in the NVIDIA developer blog. And basically, we provide like a data set for downloading, basically data set downloading links and pre-processing script to convert into Kitty format, which is required for TLT. And then we also provide some of the Jupyter notebooks. So basically, all in all, I'm just giving you an example how fast you can do deployment, like efficient deployment of deep learning model on NVIDIA embedded platform, Jetson platform, basically. So what you do is, so the workflow is basically first we download the data set and convert into Kitty dataset format. We then download the pre-trained model from NVIDIA GPU cloud, basically. We start fine-tuning model using API called TLT train with the input provided as train spec, in the train spec consisting of all the data config, model config, training config. We check if we get a satisfactory accuracy. If not, we check out another model where or increase the backbone complexity, that is switch to ResNet or 18 or ResNet 50 or 101. If you get the satisfactory accuracy, we perform pruning using simple API as TLT prune, which takes an unpruned model as an input, and then you specify a threshold. So once we prune, we retrain using TLT train API. If the accuracy is reduced, we increase the threshold, that is decrease the prune ratio. And this is basically an iterative process where you keep performing train, prune, and evaluate till you meet the desired accuracy and FPS on the Jetson embedded devices. Okay, so here is the quick example of pruning threshold versus accuracy of trained model. We can see there exists a trade-off between the pruning ratio versus the accuracy of the model, right? So table shows with an unpruned model, we could get 125 FPS on GPU, whereas 30 FPS on deep learning accelerator, which is a specific hardware for in the Jetson platform. So once we pruned with about 0.88 prune ratio, that is using only 12% of the trained model, we could achieve up to 2 to 3 times improvement in the performance, right? So here are more insights from the workflow. So as I said, this is basically it's an iterative process. So I'm doing training on single V100 data set, and I'm changing the backbones to understand what will help me. And then you can see with the ResNet 10, I'm getting MAP of 83.1, whereas in ResNet 18, I'm getting 85.5 with a similar batch size. Again, the training time varies according to your model. And then these results are basically achieved with the 4,000 images only, right? And eventually, like the inference results on NVIDIA Jetson platform, right? So in summary, I think so for efficient resource efficient basically deep learning inference deployment, you need end-to-end optimization, and techniques such as basically quantization, pruning. These are the state-of-the-art techniques which can reduce your memory transfer and compute efficiency, right? So Jetson allows basically easy deep learning model deployment with the various frameworks, and tools such as basically TensorRT will help you like post-training model optimization. So NVIDIA, another thing is NVIDIA brings end-to-end workflow for training and inference model optimization. That is with a TLT, with a data augmentation library, TensorRT, all of this stuff. So I think if you guys have a question, you can reach out to me after the seminar as well. And I think that's all from my side. Thank you so much for the opportunity. And I think we are open for question and answer.
Yeah, feel free to either put your question in the chat or unmute yourselves. You should be able to now.
I have a question.
Mm-hmm.
So you mentioned the comparison between PTQ and QAT in terms of accuracy, actually. So I was wondering, have you tried to compare in terms of latency between these two tech approach in one of these Jetson devices?
So eventually the PTQ. So I think we are talking about this slide, right? So eventually the PTQ or QAT will actually give you a model which is indate specific, right? So basically you are optimizing for indate. So right. The model latency will be similar from PTQ or QAT.
Yes. So right, but the amount of time you spend for pre-processing QAT is more than PTQ. Is it important at all for a company, or for example? Yeah, that's what is your opinion? What do you think about it?
Yeah, so I think in PTQ, it depends on how much threshold you have on accuracy. basically. So let's say if you're okay with reducing up to 1%, right, in accuracy, you can easily do PTQ, and the PTQ is the fastest. Basically, you're doing the method, like you're doing after training, so you're not wasting time in training. Whereas if you have like a stringent requirements on accuracy, like if you have a health application or robotics application, right, where your the accuracy requirements are high, in that case you can't lose like even a 1% or 0.5% of accuracy. So you want to do the QAT in that case, and there you will actually basically the training time will increase, like mostly in like if you see here with the TLT, I keep basically the retraining time is about 75 minutes. So even though you have pruned the model now, or sorry, your model is now in Tate or some or FP16, you still need to do the retraining. So that takes like more time again.
Right.
So yeah, so there is definitely a trade-off between accuracy versus a training time, and that depends on like what your application is.
Thank you.
Yeah.
Any other questions? Feel free to unmute or type your question in the chat.
I had a question.
Yeah.
Can you hear me? Yeah. So about the QAT, I'm like, here you explain based on the NVIDIA Jetson and GPUs, right?
Yes.
Jetson board and the. So if we are designing a, custom hardware, so that will require, the hardware becomes complicated, right? When you because you need to different type of multipliers when you need 32-bit and the lower bit. The quantized size, whatever size you are considering. So the hardware becomes complicated, and it requires more other detail, the timing also actually increases, right? The time to train and everything. So why would we consider going towards QAT instead?
So QAT, the whole idea of going to QAT is basically improving in accuracy. So with the PTQ, these are like most of the cases I cover here are state of the art, but you can see that it can actually go up to 2% down on the accuracy, which is basically the transformer. Basically, here is the language model transformer. So which basically can contribute to the like really bad sentence forming or like bad on accuracy. So if you want to improve the accuracy, then you would like to go for a QAT, right? That's the only thing you would like to, like that's the only why you want to go for QAT.
So have you, so basically QAT requires a pre-trained model, right? So that is basically trained on a floating point 32-bit precision, right?
So PTQ would require that. QAT, you will do the fine tuning anyway. So you can actually start fine tuning on ImageNet dataset or any other basically trained model. It doesn't need to be trained for your own application, basically.
Okay.
So you can, for starters, you can just take the ImageNet trained model and then start fine tuning for your application while doing the QAT, basically.
Thanks.
Yeah.
We have time for one more question if someone would like to ask. It looks like we have one in the chat. Scrolling up here. Bilal, would you like to unmute and ask, or?
Hi, so I was wondering, how do you determine which layer contributes the most to accuracy when you're doing quantization? You mentioned like sometimes you might want to use mixed precision for some of the layers, and for other layers you wouldn't want to use it.
Yeah, so I think so most of the PyTorch or TensorFlow, you can actually get the accuracy layer wise. So that's what we do most of the times. So you can just get the accuracy for each layer. and like how much is the difference between your float 16. So there's like a completely a DSP technique where you're basically trying to understand layer-wise statistics for each layer. You're trying to understand how much I lost due to the quantization, and then how much it's affecting to your end accuracy. So so in most cases, PyTorch and TensorFlow can actually spit out this information for you.
Thank you.
Dr. Kulkarni, thank you so much for your excellent presentation. We really
Yes.
appreciate it.
Yes, thank you so much for giving me opportunity to present in front of students at UTSA.
Awesome. And thank you everyone for attending. Enjoy your spring break if you're UTSA affiliated, and we'll see you back on the 19th of March with a presentation from Dr. Amanda Fernandez. Thanks.